Hi everyone, welcome to CNTC Zoom seminar today. It's my great pleasure to introduce Professor Masaki Oshikawa from ISSP of University of Tokyo as a seminar speaker today. Masaki did his PhD in University of Tokyo with Komoto, the K in the TKNN number. He was also a research associate with Nagaosa. After finishing his PhD, he moved to Canada working with Ian Affleck. And then he moved back to Japan ever since. Masaki has made many groundbreaking contributions to the field of a strongly correlated system, including generalizing the Lipschutz matrix theorem to higher dimension. Today, he's going to tell us about non-Fermi liquids in two-dimensional conducting network. And please, Masaki.
Thank you. So thanks for joining the seminar. It's a pleasure to visit Maryland, although just virtually, where I hope in near future, maybe next year or next I can really visit you. Anyway, today I'd like to talk about non-Fermi liquids in 2D conducting networks. And this work is in collaboration with Jonjun Lee and Gillian Cho at PostTech. And actually the main body of work for today's talk is still in preparation. Hopefully will appear in archive in a few weeks. But this is also based on our previous work on network, which is published in TRL this April. So yeah, actually I will also quickly explain this previous work on the flat band. Because this is our motivation to consider non-Fermi liquid behavior in network system. Okay, so this is one subject of our approach, tantalum disulfide. So this material has been studied for a long time, and at very low temperature, the ground state is found to be some kind of charge density wave state, but with some complicated structure. So the periodicity is square root 13 times square root 13. So it has this David star-like structure. So this is charge density wave state. So this is basically insulating state. Okay, so this is actually a Mott insulator, but you can melt this charge density wave order by going to finite temperature or applying pressure or doping and so on. And so these are phase diagrams of this tantalum disulfide. So at ambient pressure, at low temperature, you have charge density wave Mott insulator. But by applying pressure, you melt this CDW order and you enter the new phase, which they call nearly commensurate CDW phase. And by going to even higher pressure, the system basically becomes a metal. And similar phase diagram is obtained also by doping.
Masaki,
so first,
can I ask you a question?
Yeah.
This is Shankar. Is this charge density wave Mott state, is it antiferromagnetic or it doesn't have any magnetic properties?
So this is, yeah, I think this is also subject to, the debate. So there is, I think that there is a picture that each David star has spin 1/2 or something, but as an entire system, this may be a spin liquid. So each island has spin 1/2 and they are interacting, so it's not trivial system.
I was asking, what is the experimental status? Do they know experimentally if the Mott state is antiferromagnetic?
So they don't see clear antiferromagnetic order.
Okay, all right, thanks.
Yeah. Okay, then then another interesting aspect is that by going to very low temperature, actually this superconducting TC is multiplied by factor of 10 or 30. So actually it's very low temperature, but very low temperature, they find superconducting phase. So there is something interesting going on at this melted mode insulator or nearly commensurate CDW phase. And also by applying the gate voltage, they found a similar phase diagram. Okay, so we want to know what's going on in this nearly commensurate CDW phase. So until recently, it's not very clear, but last year, this is a paper from Postec group in Korea. So they measured this NCCW phase by STM. And in this nearly commensurate CDW phase, they found a clear domain structure like this. So inside each domain, they have basically the similar order as in the CDW phase. But this domain and this domain has the same kind of order, but the ordering pattern has mismatch. And each domain has the diameter of around 70 angstrom, which is pretty large. And this is an enlarged picture from STM measurement. So you can identify this ordering pattern in each domain. But this is the ordering pattern in the next domain. So in each domain, these David stars are spaced regularly. But at the domain boundary, there is a crash of David star. So here you have higher energy due to this David star sitting next to each other. So you can figure out the ordering pattern in each domain and identify where is the domain boundary. Okay, and in this NCCDW phase, you have higher conductivity. So we want to understand how the electrons are flowing in this NCCW phase. And this is our model. Oops, sorry. So within each domain, as I said, the ordering pattern is like a CDW phase. And CDW phase is basically not insulator, so it's not conducting. So the natural guess is that the electrons are conducting along these domain boundaries. So if we take very simple view, then we can build an effective model for electron degree of freedom in this NCCW phase. That is electrons moving just along the this domain wall, one-dimensional segments, and then scattered at this junction. So this gives us electrons on honeycomb network. And at first, we can try to understand what happens in a free electron system on this honeycomb network. So this looks, this looks very much like a familiar honeycomb lattice model as we encounter in graphene and so on, so on. But actually, this model is rather different because in standard so-called honeycomb lattice model, electrons can present only on the vertices of the honeycomb lattice or sites. But in our model, electrons can travel freely along the these edges of honeycomb lattice. So they are quite different. And the simple way to model this system is to discretize further these edges of honeycomb lattice. Then you can replace this network model by tight binding model, but many sites along the edge. So many sites between every vertices. But once you discretize, you can easily obtain the spectrum of this network model, at least for free electron model. And then what we find for free electron system is, okay, we find a lot of bands, but we find cascades of flat bands, so infinite number of flat bands. And we also see the Dirac type dispersion relation, but it intersects with flat bands. So this is something called relativistic spin 1 Dirac fermion structure, like this. And so we didn't expect this, but actually once you find this, it's easy to understand why we have flat bands. So basically, this flat band state corresponds to the localized eigenstate of the Hamiltonian. And for each hexagonal bracket, elementary bracket of honeycomb lattice, you can build a plane wave state like this, so that the node of this plane wave matches the vertices of hexagon. Then what happens is that for this plane wave state, the amplitude is 0 at the vertex. So electrons cannot go out from this bracket. So this is localized eigenstate, and it can be exact eigenstate of the network Hamiltonian. And you can put this localized plane wave in each bracket. So this gives flat band that is energy independent of the wave number.
Masaki,
yes.
I have a question on this.
Yes.
So typically the wave function, they can hop to other link through the junction. So here, I suspect you must have some particular pattern of your wave function at different links such that the outgoing probability is identical to 0.
Right, yeah.
So is that similar to like the Kagome that is a hopping model? You also have flat band and you can design.
Yeah, so yeah, it's similar in that respect, yes. But I'm just going to argue that the characteristics of this network model is that this flat band is more robust compared to other known cases of flat bands.
Okay.
Masaki, actually,
Yes.
this is a follow-up question. So what is if I wanted to make this a little more precise, I'd want to define scattering matrices at each of the vertices. So I guess that somehow implicitly you must be assuming some form of the scattering. So at each vertex there is presumably another line, right? Like another edge going on. So there should be a scattering matrix.
Yes.
I guess you'll talk about it later, or?
Yeah, I will discuss that later for transport problem, but
okay, but maybe I guess it's what I'm wondering. It's not obvious. Maybe it is obvious, but even if I'm not thinking about transport, even if I'm just thinking about the wave functions, more quantitatively, I want to think about some kind of scattering matrix.
Right. Yeah.
Like
okay.
here,
so
we're implicitly assuming that if the wave function vanishes at the node, it doesn't go into the third leg, which is intuitively sensible.
Okay. So your question is whether we can prove the flat band for generic S matrix here. Okay.
Yeah.
Yeah, I think it's still the case, but okay. Yeah, I admit that I haven't proved that yet. Yes, maybe that's interesting question. Yes, yeah.
Hi,
Masaki. Yeah. Yes.
Can I ask a question about because like in your previous slides, I saw the spin 1 Dirac fermion had a very interesting dispersion. It seemed that it had like a 3-4 degeneracy in the energy dispersion. I'm wondering if that degeneracy is like symmetry protected, like just like it respects some, it occurred because of some irreps of the crystalline symmetry group, or it just happens accidentally?
Yes, I think it's protected by symmetry, and Actually, this flat band is also protected by symmetry. And this spin-1 Dirac point is also protected by symmetry, but I don't remember now what exactly was symmetry protecting this degeneracy, but I agree that this is symmetry protected.
Okay, thank you.
Excuse me, Masaki, can I ask a related question about the cones?
Yeah. Yeah.
So it's a related question. So you know that in terms of flat bands, you know, sometimes, you know, if the cone is actually a true singularity, you cannot. It means that you cannot remove the upper and lower bands without you know, destroying the flatness of the band. And whereas in certain cases, just it happens to be crossing there, but then you can, for example, you can freely shift the upper and lower bands while retaining the flatness of the central bands. So which situation does it correspond to here?
Good question. Okay, again, I don't have really exact answer, but at least empirically, yeah, you cannot remove this degeneracy without spoiling the flatness. And yeah, I don't know exactly why yet.
Okay, thanks.
Thank you. So yeah, we have a bunch of flat bands, and okay, so flat band is, I don't think I have to say this for you guys, but flat band is quite interesting because the flat band is a limit in which the kinetic energy is suppressed, so the correlation energy becomes dominant. So flat band provides interesting platform to realize strongly correlated physics like ferromagnetism and superconductivity and so on. And there has been a lot of you know, flat band models proposed, at least theoretically, like this Tasaki lattice. This is to realize ferromagnetism rigorously. But usually flat band models require some fine tuning of parameters. And probably you are familiar with deep lattice, which generates flat band thanks to the imbalance between the number of sites in the sublattices. So that looks like a stable, but once you introduce longer range hopping, then you break the bipart tightness of the lattice. Then deep lattice, flat band in the deep lattice is not stable against the inclusion of longer range hoppings. But this flat band in the network model, Honeycomb network model, is more robust. For example, we can introduce inner domain sites with maybe higher chemical potential. So the low energy effective model can be written only using the network, but there are virtual processes in which electrons hop from this network part, domain wall, to inner domain sites, then hop back to the network. Then it effectively induces long range hopping. But okay, so this figure is not very clear, but what we found was that even if you include the inner domain sites, the flat band is still robust. So this is the original flat band. This is the original flat band. And these are from the inner domain site. So it's robust. And also we can check more directly by introducing the longer range hopping. So this is again network model. And now the original network model contains only nearest neighbor hopping, but you can introduce second nearest neighbor, third nearest neighbor, fourth nearest neighbor hopping onto this discretized network model. And even if you include longer range hoppings, flat band is still almost completely flat. So this flat band is more robust against inclusion of longer range hopping. That is the property not seen in other popular flat band models like deep lattice. So we hope that this is one interesting platform to realize flat band physics, because this is more robust. And again, we didn't expect this before doing the calculation. So we are kind of surprised. But once you see this, it's easy to understand why this is so robust. The reason is simple. So I just explained what is the localized state, the flat band state in this Honeycomb network model. That is a plane wave with the nodes matching the vertices of this hexagon. But now, let's say I introduce a second nearest hopping, second nearest neighbor hopping like this. And then the wave function of the standing wave state is non-zero at this site. So the standing wave state has amplitude 0 at the vertex. That's how I constructed the localized state. But the amplitude should be non-zero here. So if you include second nearest neighbor hopping, then electron can escape from this side to this side by tunneling. Then this electron can, escape anywhere. If that happens, then the flat band is no longer flat because it's delocalized. But the point is that as long as you keep the symmetry, like reflection symmetry about this axis, then the hopping from this side cancels with hopping from this side, because they have the same magnitude of wave function, but the sign is opposite, because you have node here. So the wave function must be asymmetric. The standing wave, localized wave function must be asymmetric with respect to reflection about this axis. So the hopping from here is cancelled by hopping from here. So even if you include a long range hopping, electron still cannot escape. So the flat band remains still flat. So this mechanism is broken if you include very long range hopping, which is beyond the length of the segment. So if electron can hop directly from here to there, then electrons really can escape because there is no cancellation anymore. Or if you break the symmetry, this reflection symmetry, then this hopping and this hopping is no longer cancelling with each other. So in that case, electron can escape. So this is kind of symmetry protected flat band, as long as the hopping is sufficiently short. And in case of tantalum disulfide, which we are discussing, as I said, the domain size is around 70 angstrom. So it's pretty large. So of course, beyond 70 angstrom, maybe tunneling amplitude is not exactly 0, but we can expect it pretty small. So that means that this flatness must remain good in realistic system, as long as you keep this crystal symmetry. Okay, so yeah, this is not my main subject today, but okay, this is actually a controversial subject, but one optimistic scenario is that in this flat band, if you naively apply BCS type approach, kind of mean field approximation, then the superconducting gap is enhanced compared to the usual Fermi Liquid, basically because the density of state at the Fermi level is diverging if Fermi level happens to be at the flat band. So, okay, so this is controversial subject. Actually, I don't know true answer, but there are some theories supporting that this flat band might help superconducting order. And this might explain these superconducting phases universally seen at very low temperature, starting from this nearly commensurate CDW phase. Okay. And okay, so this is our motivation to consider network model, but this kind of network seems to be more widespread. So probably many of you are working on this twisted bilayer graphene or related moire superlattice structure. But if you have, okay, I'm not expert on this subject, but this twisted bilayer graphene, the stacking pattern between two graphene layers can be classified like these patterns. Then you can define a kind of domain corresponding to each stacking pattern. And then you can see the domain wall structure, which forms a network. And this is seen in this paper using anti-fermi. This is some imaging technique using AFM. And you can see this network structure. So if electrons are traveling along this network, we can maybe apply the similar kind of theory framework. And so this is somewhat different material, but a similar material to tantalum disulfide I introduced. So this is titanium diselenide. And so this, we think we can apply the similar framework. And in this material, they interestingly observed the non-Fermi liquid transport. So this is standard characteristics of non-Fermi liquid transport. So they measure the resistivity as a function of temperature. And then you see the power of behavior, the power of dependence on the temperature to exponent alpha. And then this exponent alpha characterizes non-Fermi liquid transport. And so these are two different sets of experiments on the same material, titanium diselenide. But this one is under pressure, and I think this one is under applied gate voltage, changing carrier density. And they both found a non-Fermi liquid behavior, but with different exponent. But the interesting point is that apparently this exponent alpha depend on parameters. Like here they change the pressure and change the temperature and fit the resistivity to this power law. And in this pressure experiment, this exponent seems to vary between 2.5 and maybe, 3.2. And so in this picture, it's color coded. Sorry, but here they change carrier density and change the temperature between 15 to about 100 K. And in this region, this exponent alpha is around 1.0. And in this region, it's 2.0, so close to Fermi liquid. But here they found exponent 1.0. But it seems like this exponent is continuously varying depending on pressure or the carrier density. And we think that this material is different from the first material I introduced.
Hey, Masaki, yes. I have a question. Yes. This is Shankar. Yes. Can you expand a little bit on how this exponent is precisely measured? Is it just from transport? I mean, obviously it's an effective exponent, but I always worry when I see an exponent.
Right. Yeah, I agree that this is always tricky to determine the exponents. Yeah, I think they just fit the temperature dependence or resistivity.
So this is this n, right? That's all that's been plotted, right?
Yeah.
N.
Yeah.
But do you know a little bit more details, like over what range of temperature we are talking about this? I'm sure I can replot it and get a different dependence, okay?
Right, yeah. Where
Anyway, continue, but I think there are some issues here one should worry about.
Right, yeah. So I agree, yeah, this is very tricky business. So sorry, I don't remember.
No, that's all right. I just, for your purpose, it doesn't matter. Please continue.
Yeah.
Thank you.
Okay. So yeah, this is at this point just our motivation. So actually, I'm not going to really explain this without quantitatively, but I want to propose one, possible scenario to produce this kind of non-Fermi liquid behavior. But at this point, we are not yet at a point, I can really theoretically predict what exponent you have under certain pressure or anything. So, yeah. So to that, yeah, our theory also needs more improvement, and also maybe in experiment you have to be careful about the interpretation. I agree. Thank you. So okay, so this is just motivation, but this motivates us to consider what can be the transport through the network can look like. So what we want to consider is, okay, so in case of Honeycomb network, so we have network like this, electron can propagate and then scattered by this junction, and then go to next segment and then scatter again, and so on, so on. And what kind of resistivity or resistance or conductance we can expect from this kind of network. So one very basic element of the theory is Landauer formalism. Many of you are familiar with this, but actually I kind of started learning about this to study this network problem. So this is the most basic setting of Landauer formalism. So you have one-dimensional channel, very narrow wire you can imagine, and then you place a single scatterer barrier, and then you connect this wire to reservoir, like a big piece of metal, and one side is set to voltage 0, and one side is the other side is connected to some battery or something. So this reservoir is set to voltage V. And then the question is, what is conductance or resistance of this system? And so this scatterer may be characterized by quantum mechanically by unitary S matrix. So R is the reflection coefficient and the T is the transmission coefficient. And then this is unitary, so absolute value R square plus absolute value T square must be 1. And the transmission probability for this single barrier is given by absolute value T squared. And I'm not going to review the Landauer argument itself, but if this barrier is characterized with this S matrix and the transmission probability PT equals to absolute value T squared, then the conductance of this system is given by E squared over H times this transmission probability. Yeah, and the resistance is just inverse of this conductance. So one interesting question is, okay, so if you have finite resistance, then if you apply voltage, then there must be energy loss due to Joule heat. The Joule heat is produced like resistance times current squared. So you get the finite Joule heat generation. But this scatterer is characterized by unitary S matrix. So there's no energy loss at this scatterer or in this one-dimensional channel. So it looks like a paradox, but the answer is that in this formalism, the electron enters this one-dimensional channel with some finite energy due to this reservoir voltage, and then transmits to the other voltage. So electron is carrying the energy. So the hidden assumption is that this reservoir is summarizing. So the electron entering the reservoir is losing energy. So Joule heat is produced inside the reservoir, not at the scatterer or in this one-dimensional channel. So this is initially confusing aspect, but it's how the Joule heat is produced in this setting. Okay, so this is very well-known basic setting. So now I want to understand what happens in 2D network, but before that, let's discuss 1D network. So I have one-dimensional channel, then each segment is connected by these junctions, and each junction acts as a scatterer. So let's say I model, let's say this system is uniform, so each scatter is the same. So each one is characterized by the same unitary S matrix like this. So if you solve the scattering problem in this network quantum mechanically, then actually this is not so trivial, because you must take multiple interferences into account, because the electron can just transmit through this junction, or transmit, then deflected back, and reflected back again, and so on. So there are many possible paths, and you need to take the interferences into account. And maybe the next simplest case to the single barrier is the double barrier case. And in this case, let's say we have two identical barriers characterized by the unitary S matrix. But if you have incoming electron with certain momentum k, and if the distance between these two barriers are, L, then electron gain a phase shift k times L. So depending on the momentum of the electron, the interference becomes different. And this two barrier problem can be solved easily. And the total transmission probability looks like this. So horizontal axis is this phase shift, so proportional to the wave number. And the vertical axis is transmission probability through this double barrier. And for this, I chose deflection coefficient to be 0.9. So if you have single barrier, the deflection probability is 80%, 81%. So it's very deflecting, just a small transmission probability for single barrier. But once you take the multiple reflection and the interference into account, then transmission through double barrier can be enhanced. So this is nearly 100% transmission at certain phase shift. So this is example of resonant transmission. Okay. So then we can extend similar calculation to many barriers. So longer network, 1D network with many junctions. So this is more non-trivial, but actually you can solve this exactly. So this is like a good exercise for quantum mechanics. Anyway, so for, let's say, 100 barriers, if you plot the total transmission probability through 100 junctions as a function of phase shift, then it looks like this. So it's very weakly, because you have many resonances of order of 100, because you have 100 junctions. But for certain range of phase shift, that is certain range of momentum or certain range of energy of incident electron, the transmission probability is almost zero. So actually in this region, the transmission is exponentially suppressed. And in this region, there are many complicated structures, many resonances. But in this region, the electron can transmit through barrier. And actually this range of momentum or energy corresponds to the conduction band. Oops. So actually by solving this transmission problem, you can see the band structure of electron. So band gap or conduction band. And so this transport through 1D network in pure quantum mechanical limits has two behaviors. So if energy or momentum of incident electron is within conduction band, then you find a coherent ballistic transport. That is, conductance is order of 1. By order of 1, I mean, even if you go to very large number of barriers, this is order of 1. On the other hand, if the energy or momentum of electron, incident electron is within the band gap, then system is highly insulating because conductance is exponentially suppressed, like e to minus some coefficient times n. So this is nice, and this is exact for quantum mechanical problem. But this is different from what we normally expect as the property of material or at macroscopic scale. So macroscopic objects, the resistance should be proportional to the length, but the quantum mechanics does not produce this kind of behavior, at least in this simple network model. Yeah, of course, there are a lot of models which you can compute resistance, but in this context of network model, we can consider a certain limit easily. That is, in the previous discussion, we just solved the purely quantum mechanical problem. So electron transport is completely coherent. Then you need to take multiple reflections and the interference among different passes into account. But in reality, electrons interact with phonons and so on, so they summarize. So of course, this dissipation or decoherence rate is finite. So it's interesting to consider what happens on the finite rate of decoherence and so on. But here we consider one simple limit. That is, within each segment of this network, we suppose that the electrons interact with phonons, for example, sufficiently so that the electrons within each segment summarizes. So within each segment, electrons are in equilibrium state almost. Then you can define local voltage for each segment n. So for segment n, you can define local voltage Vn. Then you can apply this Landauer formalism because each segment now acts also as a reservoir because of this summarization. Then the current between the segment n plus 1 and the segment n is given by this Landauer formula, E square over H times T square times this voltage difference. But because the current is conserved, in the steady state, all the junctions must have same current flowing through. So you can equate all the current. That means that this voltage drop must be the same everywhere. So if you have n barriers and total voltage drop as V, so the voltage of one end as V and the voltage of the other end as 0, then total voltage drop is V. Then under this assumption, the voltage drop at each junction must be V over M. So that means that the conductance of this system in this limit, must be E square over H times small t square divided by N. That means that the resistance is proportional to the length. So this is natural behavior we expect from a macroscopic object. But interesting in this model, still what determines the resistance is this quantum mechanical property of each barrier. So this T square is a transmission amplitude or transmission probability of each barrier. So this is determined quantum mechanically. And within this assumption of summarization of each segment, it can be related to the macroscopic resistance. So this is in some sense, generalization of, well, this is a kind of generalization of Landauer approach. And you can also naturally generalize this to 2D network. And if you have two-dimensional network and length L and width W, and you apply voltage uniformly to this side and the voltage 0 uniformly to this side, then you can see that the resistance is proportional to, well, again, if you assume each segment is summarized, and if you consider free fermion, then resistance is proportional to the length and inversely proportional to the width. So this is what we learn in maybe high school physics. Actually, I did not know the name, but this is called something called Pouillet's law, according to Wikipedia. But again, this coefficient can be determined by quantum mechanical scattering property of each junction in this model. And in actual application to various materials, each segment is pretty long, like 70 angstrom or something like that. So the summarization.
Masaki, this is Shankar again. May I ask you a question?
Yes, sure. Yeah.
Yeah. So maybe I was not paying complete attention. This is one problem with Zoom talks. You know, an email comes and you get distracted. But is this all non-interacting? Because that standard Landauer is non-interacting. Pouillet's law is non-interacting. So, but, or should I kind of believe that even in the presence of interaction formally, these formulas are correct?
Okay, so far I have been discussing non-interacting cases.
Okay, good. All right.
But,
then I understand
everything. Okay. Yeah. From now on, I want to extend this to interacting cases. Yeah. Thanks. Yeah.
Actually, sorry, this is Jay. Sorry, I mean, Pouillet's law is Pouillet's law is classical, basically.
Yeah.
So it's actually thermodynamic. It's not non-interactive.
Yeah, no, I was saying about Landauer. I was saying about Landauer. Pouillet is classical. I thought it's Ohm's law.
Exactly.
Yeah. But okay, so this problem, this setting we are using is kind of okay. So we started from quantum mechanical scattering problem, but this network is in a sense classical because we introduced summarization within each segment. So electron lose coherence within each segment. So under this assumption of summarization, the transport of electron becomes diffusive. So that's why we obtain the classical transport property. Yeah, actually, I'm now trying to understand how this crossover from quantum mechanical transport to classical transport occurs by finite decoherence. But for today, I want to discuss kind of strong decoherence limits in which the electron completely loses the coherence within each segment.
Masaki, can I ask a question on this slide? So in the 1D example, it's clear you already explained how this works in this more like a higher temperature limit. Everything is thermalizing. But for network, at least I have a problem to visual how I should contrast those conductance or dissipation via the tunneling, the transmission in the 2D network because I have multiple directions.
Oh, okay. Yeah, it becomes a bit complicated, but as long as that's why I didn't show the coefficient here. But as long as so here I implicitly assume that the scattering is symmetric to left and right, and then the current flowing to from this junction to upward is cancelled by a current coming downward from this junction. So you can solve. So for symmetric scatterer, the vertical current cancels out. So non-zero current is all horizontal. So you can easily derive this.
Thank you.
Yeah. Okay. So this is related to Shankar's question. So far I have only discussed transports through network, but this network is made out of free fermions, although I implicitly introduced interaction with phonon or something so that electrons summarize within each segment. But now I want to include electron interaction because it can be, of course, important. Then the natural model is that we still use this network model, but now we model each segment by Tomonaga-Rattinger liquid. And as probably most of you know, Tomonaga-Rattinger liquid is just a low energy effective field theory for interacting electron. It's free boson field theory, but contains a coupling constant, so-called Rattinger parameter K. And all the critical exponents depends continuously on this Rattinger parameter. And free fermion corresponds to particular value of Rattinger parameter in this convention K equals 1. And if you have repulsive electron interaction, then Rattinger parameter is renormalized to less than 1. And there is a seminal paper by Ken and Fisher a long time ago. They studied transport through single barrier in Tomonaga-Rattinger liquid. And if you have repulsive interaction between fermions, then K is less than 1. In that case, even very weak barrier, very small backscattering is relevant. So if you go to lower and lower temperature or lower energy, then the system is gradually renormalizing to disconnected wires. So in the zero temperature limit, the conductance goes to 0. And not only that, they predicted exponent, how conductance goes to 0 as you go to 0 temperature. So this is their answer. So conductance for single barrier is proportional to temperature to 2 over K minus 2. So if K is less than 1, this exponent is positive. So as you go to 0 temperature, this conductance goes to 0. And this was confirmed in quantum Hall edge state and so on. So this is established result. But this behavior occurs because this barrier is relevant perturbation. So, and then if you go to 0 temperature limit, then these two wires are disconnected. Then tunneling between these disconnected wire becomes irrelevant perturbation. So they it's denormalized down to 0 as you go to 0 temperature. And that denormalization group behavior is reflected in this power law behavior of conductors. Okay, and we are interested in, for example, the honeycomb network. Then honeycomb network is consists of Tomonaga-Rattinger liquid segment and this so-called Y junction, the junction of 3 Tomonaga-Rattinger liquid. And this kind of Y junction of Tomonaga-Rattinger liquid I studied a long time ago. And we studied various properties, but maybe most physically relevant case, the case with most application to electronic material would be repulsive electron-electron interaction case. In that case, Rattinger parameter K is less than 1. So in that case, the physics is very similar to the Kane-Fisher single barrier in Tomonaga-Rattinger liquid. So in this case, again, disconnected limit is stable with respect to linearization group transformation. So generically, you expect the conductance to go to 0, and then tunneling between different wires, different segments becomes irrelevant perturbation, and you can derive the scaling behavior of the effective hopping, and then you can derive the effective the conductance as a function temperature for each junction. So this is conductance for each junction. So this is basically the same power law behavior as a single barrier problem of Kane-Fisher. But now our point is that this power law conductance of single junction can be translated into the conductance of entire 2D network using the same argument. If the tonal Rattinger liquid in each segment is summarized, then you can define voltage for local segments for each segment, and then apply this current conductance relation to each junction. Then what we obtain is that the diagonal conductance. So if you apply electric field in one direction, you can induce current in the same direction. So this diagonal conductance is proportional to the conductance of single Y junction. And we know the power law dependence of this. So if we use that picture, then the conductance of entire 2D network, Honeycomb network, behaves like this power law, this temperature. So this is the same power law dependence as the conductance of single Y junction. But our point is that the entire network shows the same behavior. So this is this means that the resistivity is proportional to T2 minus 2 over K plus 2. That's a negative power of K for repulsive interaction. And this is nothing but the non-Fermi Liquid behavior as a 2D network. And as you can see that this exponent, often called alpha, resistivity exponent, now depends on the Rattinger parameter K. So in this setup, we can naturally produce this continuously varying temperature exponent as a non-Fermi Liquid behavior of 2D system from the property of one-dimensional segment of the network.
Masaki, so, I have a question. This is Shankar again. So where are you getting the continuous behavior? I mean, you started with a short-range interaction, right? So your K is non-universal, but a constant, correct?
So well, okay. So I mean, sorry. By continuous varying, I mean K can change by pressure or something.
Oh, okay.
Okay.
Sorry. The non-universality of K is what you're talking about. Okay.
Yeah. Sorry, maybe I shouldn't say continuous varying. So it's non-universal exponent.
Yeah, you know why I was confused, because if you use Coulomb interaction, then there is no K. K varies with scale, right? I mean, you know the whole story, right? I mean, So, but that's not what you're talking about here. You're talking about really changing K by applying pressure or something.
Yes. So sorry, my wording was not clear. But my point is that okay, within this framework, this temperature exponent is determined by Rattinger parameter of each segment. So once you fix the 1D model, then you know the K. But in experiment, they apply pressure and so on. Then that would change also the property of 1D segment. Then that can be modeled by linearization of Rattinger parameter. So eventually, if we can, when we are able to really predict the value of Rattinger parameter from some microscopic information, then we can really predict the temperature exponent, resistivity exponent of this non-Fermi Liquid behavior. But so far, this is just a model calculation. Okay, so I'm running out of time. So one important point is that okay, so at first I discussed a flat band issue, and then in the latter half I discussed transport in terms of network. So the question is, when this 1D picture for transport valid? We think that basically this is dictated by crossover temperature, Tx, which is given by Planck constant times Fermi velocity over Boltzmann constant times segment length. So this temperature gives temperature scale where thermal de Broglie wavelength becomes equal to the segment length. And if temperature is higher than this temperature, you can treat the transport based on the 1D property, tonal Ginger liquid. So we think this 1D tonal Ginger liquid plus RG picture would be valid for temperature above this Tx. And for this titanium diselenide, this Tx is estimated to be 30K. So the most of these experiments, temperature dependence was done above this Tx, so this is consistent. Whereas in tantalum disulfide, this Tx seems to be pretty high. So maybe you cannot easily see this non-Fermi liquid behavior in tantalum disulfide. And in our crude estimate, twisted barrier graphene Tx is maybe 70, so it's maybe marginal. I'm not sure if you can see non-Fermi liquid behavior directly from this, but anyway.
So okay. Masaki, yeah. I have a question here. Can you go back to the last nice figure? I have no problem with your estimate of Tx. It's okay, but you cannot rule out a factor in front.
Okay.
Because it's a pure dimensional argument. There could easily be a pi square or something in front of your formula. Okay. That's one comment. So all I'm saying is that basically the argument is correct, but drawing quantitative conclusions may be somewhat misleading. Okay, that's comment number one. I mean, this is not a particularly insightful comment. I try to put word of caution whenever it comes to experiment because experimentalists don't understand these things, and they run with whatever you are saying. Okay.
Yeah. Thanks.
Second comment is that more serious is that your theory, which I like very much, you take a network and show that if transport in this network is mainly one-dimensional, which depends on length, then the 2D system will behave like a Luttinger liquid as far as transport goes. I think that's a very good idea. But you do not include other possible transport mechanisms. For example, in 2D, there may be phonons playing a role also, which will compete with the mechanism you are talking about. A non-universal mechanism. And that could dominate transport, and the mechanism you are proposing may be overwhelmed by something else. You cannot rule that out. Do you agree with what I'm saying?
Yes.
Your mechanism has only disorder, nothing else. Imagine I say that I have soft phonons in my system, and two-dimensional transport is completely dominated by that soft phonon, and this power exponent n that they're seeing is somehow coming from phonons going through Bloch-Grüneisen regime and whatnot, some details. Can you rule that out? I'm just asking a matter of principle.
So you mean phonons dominated transport means the temperature dependence of resistivity is determined by how phonons couple to
yes.
Of course we need probably quantitative comparison.
That's all I'm saying, that in principle for a specific material, and I'm not suggesting you do it, and I'm not going to do it either. When you go to the 2D regime where there is where it's a model that you're assuming that 1D transport along your segments dominating your 2D physics. I have no problem with that. I have written papers like that also. But one needs to be careful that some other phonon mechanism, which is purely 2D, like phonons and so on, are not overwhelming the transport. because they will give you a power law also, and that power law will also vary depending on where you are. You know, in typical 2D, the power law varies from n is equal to 5 to n is equal to 1 as you change temperature. You know, whether you're Bloch-Dunayson or classical equipartition. All I'm saying, one needs to be careful.
Okay. Yeah, I agree. Yeah. So actually, one thing we are trying to do, not completed yet, was to make a prediction based on this network fixture on maybe more local transport, like you bring STM and measure conductance between one point and some some points not too far from the other points, and we are hoping to make more concrete prediction based on network model. Yeah, of course, again, yeah, we need to compare with other possible scenario, like what you said. Yes, so yeah, I agree that definitely this non-Fermi liquid type behavior alone does not really prove this scenario. There are other, probably many other possibilities.
Yeah, the reason I'm even bringing it up, because in your work you have a calculation, so I have no problem, that the whole cuprate literature, if you look at the cuprate literature, it's filled with, you know, all kind of claims of non-Fermi liquid without really any serious calculations, based just on seeing some exponent in transport. Often the exponent is 1. And as you know, every metal in the periodic table has an exponent 1. Okay, once you go above 40 Kelvin, every metal transport is linear in T up to 1000 Kelvin. So if I use that argument, then every metal also becomes non-Fermi liquid. Of course, then people say, no, metals, you know what you're going on. In cuprate, you don't know what is going on. So I have a little problem with just claiming some great behavior based on just the Paul law. Now, my criticism doesn't apply to your theory at all, because you have a calculation. And as long as you have a calculation, I'm happy, because I know what you're including and what you're ruling out.
Right.
But in cuprate, nobody has any calculation. So it's very difficult to argue with those people, you know, because they don't have a calculation. So I can point something out. Okay? That's my only concern. Okay. But please go ahead. I mean, sorry.
No. Yeah, it's important point. Yes. And thank you. But I'm almost done. And okay, so this might explain. I agree with Shankar that we have to be really careful before drawing any solid conclusion. But yeah, just one possibility. The other interesting stuff is that in our past work on Y junction, we also found other fixed points. For example, we found these chiral fixed points. So this is stable for attractive interaction, K between 1 and 3. And in this chiral fixed point, electron coming from, or maybe current flowing from this channel goes to this channel. So always deflected to the right. So this is asymmetric fixed point. So this fixed point has non-zero asymmetric conductance. And if you build network out of this, then you obtain whole conductance. Okay, I skipped this part, but if each junction has this asymmetric conductance, then entire network has whole conductance, which is given by this asymmetric part of the conductance. So out of this chiral junction, we can have some whole material, whole conductance of entire 2D network. And also we have strongly coupled fixed points, which give you the good metallic conductance, which is, this is also stable for attractive interaction. And also sometimes you can produce asymmetric fixed points. So this channel and this channel is connected, but this channel is decoupled. And if you align this asymmetric fixed point regularly, then you can produce a stripe kind of phase. So there are many possibilities to build 2D electron phases out of this 1D segment. Okay, to summarize, this network model may be relevant for electrons in this nearly commensurate CDW phase of tantalum disulfide or titanium diselenide, and maybe more or less super lattice. And so in terms of band structure, this structure naturally produces, especially the honeycomb network, produces robust flat bands protected by symmetries. And also this model can rather naturally produce non-Fermi Liquid type resistivity with non-universal exponent, this exponent determined by the Landauer parameter of 1D segment. So of course, we have to be careful to draw conclusion about applicability to any real material, but I hope this is one interesting direction to pursue. So thank you for your attention.
Thank you, Masaki, and now open to the questions.
Yeah.
Okay, maybe I can ask the first question. So sure. In the chiral fixed point you mentioned, is there a longitudinal conductivity in this fixed point?
Pardon me?
Is there a longitudinal conductivity when you form a network?
In this limit, actually it's 0. Yeah.
Oh. So you think it's more or less like an integer quantum?
Yeah.
Okay.
At least in this limit of.
Yeah, the reason I asked this question is I recall a paper by Chamon. He's reporting some non-vanishing longitudinal conductivity, finite hole conductivity from Y junction network a while ago. So maybe he's tuning to a different limit. Yes. Okay.
Oh, hi, Masaki. Can I ask a question? It's Jay. Yeah. So is any kind of quantum oscillation seen in these materials?
Oh, good question. I don't remember. Quantum oscillation. Maybe I'm just not aware of this, but I'm not aware of such experiment in this CDW or nearly constrained CDW phase.
I see. But this Landauer liquid picture would basically assume no quantum oscillation, right? There's no coherent. Well, actually, it's not obvious, but at least there are no coherent quasi-particles going around, so you don't expect flux.
Yeah,
much flux.
But so in our transport calculation, we assume that electron loses coherence within each segment.
Exactly.
So if that is the case, we wouldn't see quantum oscillation. Although I guess in reality, so the limit I described is just a very simplified limit of strong decoherence. So in reality, the decoherence rate is finite. So there must be some crossover between quantum coherent behavior to classical or diffusive behavior. So that's one question I'm trying to first understand theoretically, yes, but not yet completed. So eventually, we want to compare with experiment using this finite decoherence rate.
Right. Yeah. Cool. Thanks.
Maybe I can ask another question. So in your calculation about this disconnected limit at a k equals to 1, it actually has no temperature dependence. But I actually noticed that this no temperature dependence at k equals to 1 seems to be a very generic property.
Yeah.
Has this been expected or has been proved?
Sorry, I couldn't hear the last part.
Sorry, I mean that you can consider different boundary condition at the one, and you can also set to k equals to 1 and start to do like a single particle tunneling, and you can compute the dimension. And at K equals 1, can I just simply conclude that everything is temperature independent?
Well, I mean, in a ideal limit. So, so within field theory, K equals 1, it should be temperature independent. But of course, in real electron model, the transmission probability can depend on the energy. But that's the non-universal part of physics, I guess.
Oh, okay. Is there any questions?
Hi, Masaki. Can I ask you a question?
Yeah.
I think in your, in your introduction, you mentioned that for this kind of system, when you dope it or gate it, you can achieve transition from the non-Fermi liquid or this mode behavior to superconductivity. I'm wondering but if we consider a system as like a network of the lighter liquid, is there like can we achieve like say two-dimensional long-range superconducting order in terms of this kind of network of wide junctions in the system?
Okay, yeah, good question. That's another thing I'm trying to figure out. So I haven't yet have a complete answer, but so I'm not sure how much realistic it is. But if we model, if we suppose electrons are subject to attractive interaction, then each segment may be modeled by, the attractive Rattinger with Rattinger parameter k bigger than 1. So in that case, you can stabilize this strongly coupled fixed point. Strongly coupled means that the superconducting order parameter matches at the junction. So if we can realize this Dirichlet fixed point at each junction, then in a sense, the superconducting order parameter, coherently propagates through the system. So in this case, the entire 2D network can behave like may behave like a superconductor. So
like a 2D array of Josephson junctions.
Yeah, something like that. Yeah.
See, thank you.
Although to apply to this tantalum disulfide and so on, maybe it's not so realistic to model each segment as the tonal liquid with attractive interaction. So maybe for those materials, it's not maybe so simple. But as a matter of principle, if you have attractive interaction, then we can have attractive interaction tonality liquid, then we can have kind of Josephson network 2D, then it can behave as superfluid, superconductor, I think.
I see, thanks.
Okay, if there is no other question, then let's thank Masaki for his wonderful talk.
Thank you.
And I will start recording. Okay.